Hello and welcome. Today we're going to explore a beautiful and powerful idea in mathematics called the integral. Now, that word might sound a little intimidating, but I promise you the core concept is something you already understand intuitively. At its heart, an integral is just a way of adding up lots and lots of tiny little pieces to find a whole. Imagine you have a pile of sand. You could try to measure the whole pile at once, or you could measure it one tiny grain at a time and add it all up. Integrals are like that second approach, but for things that are constantly changing, like the speed of a car or the height of a curving hill. It's a tool for summing up continuous change. Let's think about a simple question. If you have a rectangle, how do you find its area? You probably said length times width. It's straightforward because the height of the rectangle is constant. It doesn't change from one side to the other. But what if the top of your shape wasn't a flat straight line? What if it was a swooping, graceful curve? Suddenly the height is different at every single point. You can't just pick one height and multiply it by the width. This is the exact problem that integrals were invented to solve. They give us a precise method for finding the area of these complex, curvy shapes. Alright, so we have a curvy shape and we want to find its area. Our trusty length times width formula doesn't work directly. So, what can we do? We know how to find the area of a rectangle. So, let's try to approximate our curvy area using rectangles. Imagine our curve is drawn on a graph. We could draw one big wide rectangle under it. The height of this rectangle could be, say, the height of the curve at the midpoint. Now, if we calculate the area of this one rectangle, will it be a good approximation of the area under the curve? Probably not. Parts of the rectangle will stick out above the curve, other parts will leave gaps underneath. What's the logical next step to get a better approximation? Well, what if we use two rectangles instead of one? We could split our area down the middle. Now we have two narrower rectangles. We can adjust the height of each one to better match the curve in its own little section. If we add the areas of these two rectangles together, our total is going to be a much closer estimate of the real area under the curve. The gaps are smaller and the parts that stick out are smaller. We're getting warmer. This is the fundamental strategy. Divide the problem into smaller, manageable pieces that we know how to solve. Now, let's take this idea to its logical conclusion. If two rectangles are better than one, what about four? If we split the area into four sections and draw four skinny rectangles, the approximation gets even better. The combined area of these four rectangles will be very, very close to the true area we're looking for. The little errors, the gaps and the overshoots, are shrinking. You can probably see where this is going. What if we use 10 rectangles, or 100, or 1,000? Each time we add more rectangles, they become skinnier, and they hug the curve more and more tightly, giving us a more accurate answer. This is the beautiful core idea behind integration. We are imagining what would happen if we could use an infinite number of rectangles. Each rectangle would be infinitesimally thin, impossibly, wonderfully thin. If we could do that, there would be no more gaps. There would be no more overshoots. The tops of these infinitely many, infinitely thin rectangles would perfectly trace the curve. And if we could somehow add up the areas of all of these infinite rectangles, we would have the exact, perfect, and true area under the curve. This conceptual leap from a finite number of rectangles to an infinite number is the magic of calculus. We've established our strategy. Use an infinite number of infinitely thin rectangles to find the exact area under a curve. But how do we actually do that? We can't sit down with a piece of paper and add up an infinite number of things. This is where the notation and the machinery of calculus come to our rescue. The concept of the integral is what allows us to perform this infinite sum. The symbol for an integral looks like a tall, elegant S. It stands for sum. When you see this symbol, think. We're about to sum up an infinite number of tiny pieces. Let's look at how we'd write this down. The function f of x, starting point a, ending point b. We write the integral from a to b of f of x dx. The integral sign is our summation symbol, a at the bottom, b at the top. The function fx represents the height of our curve at x. It's the rule giving the height of each rectangle. What about that little dx? Now that we have a feel for what an integral does, it's important to know that they come in two main flavors: definite integrals, indefinite integrals. They are closely related, but they answer slightly different questions. The one we've been talking about so far, the one that finds the area under a curve between two specific points, A and B, is called a definite integral. The key word here is definite. It's definite because it gives you a definite single numerical answer. The area under the curve y equals x from x equals 1 to x equals 3 is a specific number. It's a defined, concrete value. You can always spot a definite integral by its limits of integration, the little a and b attached to the integral symbol. These limits tell you the interval you're interested in. So, the integral from 1 to 3 of f of x dx is a definite integral. It's asking a very specific question. What is the total accumulated area under the function f of x, starting at x equals 1 and stopping at x equals 3? The answer might be 410.5 pi, but it will always be a single number. This makes definite integrals incredibly useful for practical applications where you need a final, concrete quantity like total distance traveled. Total volume, any quantity that is built up from countless tiny contributions. This concept of accumulation is the key. Think about filling a bathtub. The total amount of water in the tub is the accumulation of the flow from the faucet over time. If the flow is steady, it's easy to calculate. But if you're constantly adjusting the knob, the flow rate changes. An integral would help you find the exact amount of water in the tub at the end. This might still feel a little abstract, so let's ground it. The main visual we'll use is finding the area under a curve. This is the classic introduction to integrals for a reason. It's easy to see. We'll be looking at a graph, a line on the graph, a curve on the graph, and our goal will be to find the exact area of the space between that curve and the x-axis. Why is this useful? Well, as we'll see later, that area can represent amazing things in the real world. Like the total distance a rocket has traveled, the total energy consumed by a city, the total amount of a drug that has been absorbed into the bloodstream. This concept of accumulation is the key. It's a method of accumulation. Okay, let's dig deeper into the idea of integrals as a form of superpowered addition. At its core, an integral is, well, an accumulator. It gathers up quantities. We started with the idea of accumulating area by adding up tiny rectangles, but this concept applies to so much more. Think about processes where things add up over time. This is where integrals shine. They're the tool for summing things that don't change at a constant rate. Imagine you're driving a car and you track speed every second. First second, 5 meters per second, next, 6 meters per second, then 7 meters per second, then 7.5 meters per second. To find distance after 10 seconds, you could roughly multiply each speed by 1 second and add them. Distance for second 1 is about 5 meters, and so on, a discrete sum. But an integral does the same thing for continuously changing speed. The car doesn't jump between speeds. It smoothly passes through every value. 5.1, 5.11. To get exact distance, you must account for speed at every instant. Add an infinite number of tiny distances, speed times an infinitesimal dt. So we can find the area under a curve. That's a neat mathematical trick, but why does it matter? Integrals are a cornerstone of science, engineering, economics, and many other fields. The area under a curve often stands for something tangible. Total distance, total volume, total energy, total profit. The integral is the bridge from a changing rate to a meaningful total. Let's explore examples. Physics and engineering rely on integrals. Power consumption over time. Integrate to get total energy. Designing power grids and batteries depends on that. Engineers designing a dam need total force of water. Pressure increases with depth. Integrals sum force across depth to get total force. That's how we ensure dams hold. Bridges, dams, and airplanes rely on these calculations. Now, economics and finance. A projected revenue rate over 5 years is a model an analyst might have. That rate fluctuates due to market conditions, product launches, and competition. Let's walk through one more practical example from start to finish to solidify everything we've learned. This is a classic problem that perfectly illustrates the power of integration. Imagine you are in a car that is accelerating. You look at your speedometer. The speed can be described by the simple function vt equals sine 2t, where t is time in seconds since you started. At t equals sine 0, speed equals sine 0. At t equals sine 1, speed equals sine 2m per s. At t equals sine 2, speed equals sine 4m per s. And so on, the speed keeps increasing. How far did you travel in the first 10 seconds? We can't just use distance equals sine speed x time because speed isn't constant. Which speed would we use? At the beginning, 0m per s. At the end, 20m per s. Some average speed? An integral gives the exact answer without guessing. We want to accumulate all the tiny bits of distance for every infinitesimal moment in those 10 seconds. So we set up a definite integral. The setup: integral from 0 to 10 of 2t dt. Conceptually, 2t is the height of a rectangle at time t. dt is the tiny width, an infinitesimal slice of time. The integral sums the areas of all these tiny rectangles from 0 to 10. To solve, find the antiderivative. What function's derivative is 2t? The derivative of t squared is 2t, so the antiderivative of 2t is t squared. Evaluate t squared at the endpoints. d equals sine 10 and t equals sine 0, then subtract. Compute 10 squared. 0 squared equals sine 100, 0 equals sine 100. Units, meters. We've talked about derivatives, rates of change integrals, accumulation as separate ideas. But the most powerful and beautiful result in all of calculus is that they are intimately connected. They are, in fact, inverse processes of each other, like multiplication and division, addition and subtraction. This profound connection is captured in a result so important that it's called the Fundamental Theorem of Calculus. It's what links the two major branches of calculus together and makes calculating definite integrals practical. The theorem has two parts, but the main idea we've already used is this. To calculate a definite integral, you first find an indefinite integral, an antiderivative. Remember how we needed to find the total distance traveled when the speed was 2t? We first asked, what function has a derivative of 2t? We found that function was t squared. The Fundamental Theorem of Calculus formally guarantees that this procedure is valid. It tells us that if you want to find the integral of a function, its total accumulation, you can do so by finding its antiderivative and plugging in the start and end points. We have covered a lot of ground today. I hope you're leaving with a new appreciation for the power and elegance of integrals. Let's quickly recap the most important ideas. We started with the simple notion that an integral is just a sophisticated tool for adding things up. It's designed to find the total of something that is changing continuously, a problem that simple multiplication cannot solve. The most intuitive way to visualize this is by finding the area under a curve, which is the classic application of integration. We saw that the strategy to find this area is to fill the space with rectangles. While a few rectangles give us a rough estimate, the true magic happens when we imagine using an infinite number of impossibly thin rectangles. The integral is the mathematical tool that lets us sum the areas of all these rectangles to get one perfect, exact answer. The notation, the integral of f of x with respect to x, is a concise way of saying sum up all the tiny areas, where each area is its height, f of x, times its infinitesimal width, dx. It's a method for achieving perfect accumulation. We learned about the two flavors of integrals. The definite integral has limits, from a to b, and gives us a single numerical answer, like the total area or total distance over a specific interval. The indefinite integral has no limits, and gives us a general function, the antiderivative plus a constant c. This distinction is crucial, as is the connection between them. The Fundamental Theorem of Calculus shows us they are inverse operations, allowing us to solve definite integrals by first finding an antiderivative. This is just the beginning of your journey, but you now have the core conceptual understanding of one of the most powerful ideas in mathematics. Keep asking questions, and keep learning.